Hello guys, in this video I would like to discuss about periodicity, especially related to the structure 3.1 of the IPTP syllabus. So in this case I would like to show you a periodic table, and we usually define periodic table and place coordinates on atoms depending on the groups. So the vertical part, vertical classification, and the periods, so the horizontal classification like this. So the groups actually assign atoms based on their similarity and also based on the same number of electron valence, meaning that they have the same number of electron on the outer shell, while for the period shows that they have the same number of shells. So for example, here is period 1, meaning that they have 1 shell, and then 2 shell, 3 shell, and so on. Okay, so the rows actually are the period, and they show the number of shells, and the columns are actually the group, and they group atoms similar to their characteristics and also electron valence. Now you've learned about SPTF electron configuration. You also see that some parts of the periodic table are assigned to a specific block. For example, like group 1 and group 2, they are called the S block. So here are the S block. And in the middle part, the transition metal, they are called the D block. And then the green part, they're called the P block. And then for the specific part, the F block, yeah, we will not learn it in IP syllabus. So it's really useful, for example, because if you want to easily, let's say, assign electron configuration to aluminum here, right here. So you can just say like 1s2, then 2s2, then 2p6, because like 2p1, 2p2, 2p3, 4, 5, 6, and 3s2, and then 3p1. So means that you can just use the block to easily arrange the electron configuration. So without you needing to assign like the block one by one. Okay, so they have names, the group have names. So the ones that you need to pay attention to is like, for example, group 1. They are the alkali metal, the group 1. Why is it called alkali metal? Because the metals, if it is reacted with water, for example, then they will form actually, this is hydrogen. So an alkali, a very strong alkali or strong base. Yeah, that is why group 1 usually it's called alkali metal. And for group 7, they have also a specific name. Group 17, they are called halogen. And group 18, they are called noble gases. So I think these three, at least you should know the name of the group. So now I would like to discuss actually about some periodicity properties, because there are some increasing and decreasing trend of physical properties, physical-chemical properties of these atoms, and we need to discuss according to IP syllabus. So the first chemical properties that we need to discuss, the first physical, is actually atomic radius. So now I would like to invite you to think, for example, we have lithium 3, and then we have, let's say, sodium 11. For simplicity's sake, I would like to make the older electron configuration, which is in cells, so like 2, 1, and for Na it will be 2, 8, 1. And I invite you to think which one of these two atoms would have like longer radius. Then just from this observation, you would see that sodium, they have 3 shells. 3 shells in contrast to lithium's only 2 shells. So that is why, of course, the radius of sodium would exceed the radius of lithium, because sodium has more shells. And it's so significant in determining atomic radius. It's the first thing to consider, whether they have more number of shells or not. But then things get weird. For example, if we have same number of shells, let's say Cl287. Now in this case, that they have all 3 shells. So now we have to come into the second consideration, which is to nuclear charge, or what we call Z effective, or nuclear charge. So you know that this number is not only about the electron, but also the number of proton. So 11 here means 11 proton in the middle, and also 11 electron across the suborbitals. And then here 17 proton also. Now you can imagine that proton and electron, yeah, somehow and somewhat, they do have like attraction forces, because positive and negative charge, right? Positive and negative, they attract each other, just like the North Pole and the South Pole of the magnet, they would attract each other as well. So now we imagine that 17 protons, in contrast to 11 protons, they have their own attraction forces. Then which one would have stronger attraction force? Then I would say the 17 one would actually pull closer, so it will be pulled stronger, right? So it will be pulled more. Meaning that because the nuclear charge of Cl is more than the nuclear charge of Na, the pull is actually more in Cl compared to Na. Therefore, the radius of the Cl will be more compressed because of the attraction force, meaning that you will have a longer radius for the sodium. So the first consideration is that the shell. So you know that from the periodic table, the more you go down, the more shells you will have. Yeah. So this is only 1 shell, 2 shell, 3 shell, 4 shell. So the more you go down the table, meaning that your atomic radius will be larger. Now across the same period, like across the group, so for example, like group 4 here, if you go to the right, then you're technically adding more proton, adding more atom number, right? Adding more atom number within the same number of shell. So meaning that if you go right, then your nuclear charge will be larger, and then the attraction force will be much larger as well. So the atomic radius will be lower. Therefore, if you want to make it bigger, then you should go actually to the left. So technically, this thing would have the largest radius just from this explanation. The more you go down in the periodic table, the larger radius it will be. And for across period, across the group, so within the same period, across the group, the more left you go, because of the nuclear charge number which is smaller, it will have a larger radius. Like having less pull, imagine having less pull. That's for the atomic radius. Okay, but sometimes we also compare between ionic radius, right? So let's say that we have argon. Argon is 18. So then we have 288. And then let's say we have potassium 19. It's 2881. And you know that potassium typically form potassium plus 1 ion releasing 1 electron. Meaning that if you want to make potassium plus 1 ion, it will be just 288. And then for Cl, it's 17, it's 287. But you know that Cl actually receive 1 electron to form Cl negative 1 ion. Therefore, Cl negative 1 ion will be also 288. Now you see that these three, they have the same number of electron. Ar, potassium plus 1, and Cl minus 1. These three, because they have the same number of electron, they are called isoelectronic or isoelectron. Now, according to our previous explanation, if we want to actually decide, they have the exact number of shells. So we cannot just decide by shell, so we need to check their nuclear charge. So here, potassium, they still have 19 proton, and Cl, they have 17 proton. So the larger nuclear charge is, the higher or the larger the attraction force. Therefore, potassium plus 1 ion would have more attraction force, so it will be the least or the smallest one. Therefore, potassium plus 1, and then argon, and then Cl minus 1 ion. So in this case, technically we have a trend that a positive ion usually would have like less radius compared to its normal atom. For example, here potassium, we see that potassium, let's observe potassium and potassium plus 1. It is at 2881. So imagine that it has like 4 shells, right? But then it forms potassium plus 1 ion. It loses this one thing. So technically, potassium becoming ionized, so creating positive ion, would have like lower radius compared to the normal atom. While for negative ion, actually, they have like larger radius in general, yeah, because now they have more electrons. And imagine that these people who are actually putting up a force, yeah, to maintain the distance between electrons and the nucleus, yeah, they cannot keep up with more electron compared to just, let's just say that keeping up 17 electrons requires less effort compared to keeping up 18 electrons. So these 18 electrons would actually stray a bit far ahead. Yeah, it is maintained by the same number of polis, you can say. Yeah? Technically, positive ion would be less than the normal atom, while the negative ion would be more than the normal atom. So these are the the ionic radius in comparison to atomic radius. Now I would like to discuss the third property, which is the first ionization energy. So ionization energy, especially the first one, is actually the energy required for us to strip one electron, in its atom gaseous form. Yeah. So for example, here we have an X, so it's in gas, and then it will form X positive gas, and then releasing one electron. So this will fly away. So what is the energy required to strip this electron, yeah, from this atom? That is the first ionization energy. So I would like to also ask you to imagine, yeah, let's use this example because it's so easy. Lithium and sodium 281. Imagine that you're trying to strip one electron. You're trying to strip this thing. You're stripping it. And then like you have 3 proton here, and then you have 11 proton here. Yeah. So is it easier to strip one from lithium or one from sodium? Well, actually it's easier to strip one from sodium. Why? Because the distance from the proton to the last to the shell where actually the electron is being stripped, it's kind of far, right? Because the radius of sodium is exceeds radius of lithium. Therefore, the distance to from the nucleus to the outer shell is kind of far for sodium. Because this thing, like the one that is keeping things intact, is kind of far, so it's very easy for us to just steal this one away compared to stealing from lithium. Because lithium, well, the electron is located kind of close to the nucleus. So imagine that this is like the police station, and because lithium is the nucleus is located close to the police station, yeah, this electron is still very close to the police station, it's very difficult for a thief to come and steal this electron. Well, for sodium, because the police station is very far, it's further compared to lithium, then it's kind of a bit easier for us to steal one electron from sodium compared to stealing one electron from lithium. Therefore, we have actually an indirectly proportional relationship between atomic radius and ionization energy. Like the further your atomic radius is, the easier it is for us to strip one electron away. There can be some variation, but the variation of ionization energy and successive ionization energy is in HL level material. We will discuss that in a separate video, but for SL, what is important is just for you to know that ionization energy is the energy associated for stripping one electron away from a gaseous atom. Why does the atom needs to be gaseous? Because you know that in gas form, the atoms, the particles are far apart. So it's very easy for us to separate the atoms one by one and then to observe and study those atoms individually and separately. Imagine like you're studying a metal that are tied together, vibrating in position. So yeah, it's very difficult. So by separating them in gaseous forms, then we can study them easily. Okay, so now for similar to ionization energy, we have what is called electron affinity. So long story short, electron affinity is kind of similar with ionization energy, but ionization energy is like energy required to strip one electron away, right? But for electron affinity, it's like the energy that is produced, produced or actually required, very rarely required, but mostly like the energy is produced when one electron is actually given to an atom to form a negative ion. So for example, like you have X also in gaseous form, then you give one electron, then it will form X negative 1 ion like this. So usually the process of attachment will also produce some energy, like delta H is exothermic. They release energy usually. And how is the trend? So imagine, so I would like for you to imagine, again, lithium and sodium, they are the best example. I think it's very easy to illustrate. Oh well, maybe not these two. Maybe something yang in other group. Let's say fluorine 27 and Cl 17 287. Okay, so we know that here the Pauli station is here. The Pauli station, the proton, the 9 proton and 17 proton is here. So we know that just judging from the shell, the Cl has larger shell, so like they have more shells, so it's larger atomic radius compared to F, which has less atomic radius. So you can see that because F has smaller atomic radius, the Pauli station can see things very easily, and they have like the attraction force can easily impact this part. So like, imagine that this is the magnetic field. Just imagine. So means that the attraction force is still very strong. So once you put one electron and then like you put it here, you just feel the electron just latch quickly to the friends, to the orbits. Meaning that it will produce more energy. More energy, more exothermic here. More exothermic. Well, for Cl, because like the distance between the Pauli station and the outer shell is further, so like imagine the attraction force is actually weaker. So when you hold your electron closer to the outer shell, it will not react as violently, or it will not be as aggressive compared to F. Because for F, it's closer to the nucleus, and then like the attraction force overall is stronger there. For Cl, it's less strong, the attraction force, due to larger atomic radius. So it's kinda less exothermic. So the general trend for electron affinity is that if you go from left to right, it will be more exothermic. And if you go like from up to down, it will be less exothermic. Okay, so like up to down less exothermic means that down to up is more exothermic. So this is more exothermic. And then this is more exothermic as well. So left to right more exothermic, up to down more exothermic. So if you see this trend, actually this is kind of the opposite of atomic radius. Look at this. Atomic radius. So knowing and determining the atomic radius, sometimes one of the easiest way for us to determine the other periodicity properties. Okay, so we've discussed about the electron affinity and the ionization energy. Well, for the ionization energy, especially, we have not discussed the trend. So you see that here, going from lithium to sodium, sodium is actually easier to strip the energy. Well, for lithium, it's more difficult to strip the energy. Meaning that we need more energy for lithium. So going up, you need more energy. And going right, you need more energy as well. Okay, because like you have yeah, you can relate it to atomic radius. Yeah, the distance is very far, so then it's easier for us to strip. So left to right, you need more energy. Ionization radius, ionization energy typically increase. Down to up, also more energy. Similar to electron affinity. So left right more exothermic, down up more exothermic. Finally, we have the fifth one. It's called the electronegativity. So it's the last properties. So the electronegativity is like a measure of tendency or like likeness of an atom to attract electron and to form chemical bonds. Yeah, to form chemical bonds. Well, they have created a scale for this. So someone actually did. It's called like the Pauling scale. So the most electronegative thing would actually be located in group 7. So it's actually F with a scale of 4.0. So technically, you know that group 7, group 17, like they have 7 electron valence. So like 2, 7 here. Meaning that they really want 1 electron here, so that this would be stable, right? So F would desire electron more than other atoms, or like group 7 in general, because like they just need 1 more to become stable. Compared to group 6, they need 2 more. So if they are offered 1 electron, yeah, they okay, yeah, I can take it. I mean, like I need 2, but giving me 1, yeah, I can take it. But imagine like F, yeah, it really wants it, because like it needs 1, as it depends its life on the extra 1 electron. So typically going from left to right, from group 1 to group 17, you will have an increase of electronegativity. While going up, you will also have an increase in electronegativity. Because like here, F, you can also relate it to atomic radius. F compared to Cl, let's say, well, F is 9, Cl is 17. So like it's closer with F, like the atomic radius. So the attraction force is much higher in F compared to in Cl, the attraction force. Therefore, it's easier for F, or like if F fights against Cl, then F would surely win the tug of war to obtain this electron. Yeah, imagine like this is F, and there is an electron, and the Cl. Yeah, of course this electron would be attracted stronger to F, because the radius is less, the attraction force is much stronger, so it will be put here compared to Cl. Yeah, that's the idea. So electronegativity, the tendency or the likeness of an atom to get an electron, so to pull an electron to form a chemical bond. From left to right, it increases in electronegativity. From down to up, it also increases in electronegativity. We can discuss also about reactivity, but reactivity mostly it's more interesting in group 1 and group 17. Group 17. So group 1, I think lithium, sodium, this NFR, I think, francium. Okay, so group 1 typically likes to release 1 electron, because in their metal form, let's say that this here, 281, they would release 1 electron so that they become stable, 28. Yeah, all the electron shells are full. Now, if you see, the more down you go, the longer they are, right? Something like this. Yeah. So it's easier and easier for group 1 metals to release 1 electron if you have bigger atomic radius. Therefore, francium is actually the most reactive group 1, meaning that group 1 reactivity goes down, yeah, reactivity. As you go down, then the reactivity of group 1 metals would increase, and Fr here is the most reactive metals in group 1. While for group 17, like this, imagine, well, 27, 287, 28187, and so on. So they would like to take one electron actually. They would like to take one electron. And it's easier for us to give one electron. Yeah, imagine the magnetic field here. Yeah, imagine, just imagine. It's not the most appropriate explanation, but you can imagine that there is an invisible attraction force in F. The shorter the radius is, the bigger the attraction force becomes. So like F is the one that has the strongest pull out of the other group 17 atoms. Therefore, for group 17, the reactivity goes or like increases as you go up the group. So F is the most reactive of group 17, while Fr is the most reactive of group 1 metal. So I hope that you know atomic radius is one of the most important periodicity properties that you can use and relate it to other things as well. So for HL materials, especially for the ionization energy, we'll discuss this later in another video. But for general overview and also for SM material, this should be able to cover the necessary things. So hope that this video helps. Thank you and good luck.